Okay, in today's lesson we're talking about hydrogen ions and acidity. This is chapter 19, section 2 in your book. First of all, acidity only makes sense in an aqueous solution because water naturally self-ionizes into hydrogen ions and hydroxide ions. So what that means is if you have any aqueous solution, the water dissociates into the hydrogen ion and the hydroxide ion. Okay, water, of course, being a liquid, and the hydrogen ion is aqueous, and the hydroxide ion is aqueous. So this is what we mean when we talk about water self-ionizing. Now, if you have an aqueous solution where the concentration of the hydrogen ions and the concentration of the hydroxide ions is equal, then you have a neutral solution. If you have more hydrogen ions than hydroxide ions, you have an acidic solution. If you have more hydroxide ions than hydrogen ions, you have a basic solution. So, just a little bit of vocabulary here. Oftentimes, I will call this H+. Its actual name is either hydrogen ion, what I would usually call it. Now, if you think about what a hydrogen ion is, it's a hydrogen atom that has lost its electron. So, the most common isotope of hydrogen just has one proton and one electron with no neutrons. So when you lose the one electron, all you're left with is a proton. So some people call the H+ ion a proton because that's what it is. It's a hydrogen that's lost its one electron is a proton. Okay, you've seen the hydroxide ion before. It's on your polyatomic ion list. Okay, so it's called the hydroxide ion. Okay, now, the ion product constant for water. That's just another way of asking for the KEQ, or the equilibrium constant, since this is an equilibrium. And any equilibrium, it's the products over the reactants raised to the power of their coefficients. So this would be the concentration of hydrogen ion times the concentration of hydroxide ion. Now, since water is a pure liquid, it does not appear in the equilibrium expression. So this is the expression for what we call KW. It's just the KEQ for the specific circumstance where you have water self-ionizing. So that's all KW is. This is the KW expression. Okay, and I think I said already that an acidic solution would have more hydrogen ions than hydroxide ions. The opposite would be true for bases. Now, the concentrations of hydrogen ions and hydroxide ions, these are always small numbers, 10 to the minus something or other. So they're a little bit awkward to work with. A guy named Søren Sørensen, which is about as Scandinavian a name as you can come up with, came up with something called the pH concept. Okay, he wanted to be able to discuss acidity and basicity without those small numbers. So he came up with a system that uses the base 10 logarithm. Okay, so these are some important formulas that you want to have in front of you when you do your exercise with this. And these are formulas that you will need to know. pH is equal to minus the log, that's log log, which is a different thing than the ln log, of the hydrogen ion concentration. Now you've probably heard of pH before. You may have never heard of pOH. There is such a thing. The pOH is equal to minus the log of the hydroxide ion concentration. These two are related to each other. If you have the same solution and you find the pH and the pOH, they add together to be 14. Now, the hydrogen ion concentration, if you have the pH, well, before we do that, let's look at our scientific calculator. So you want to get out your scientific calculator and find the log, L-O-G button. On my calculator, the log button is right here. Now, don't confuse that with the LN button. LN is the natural log, and that's a completely different thing. Okay. So usually, when you find your log button, some calculators it's a second function, but usually on the same key, you'll find a 10 to the x button. So on my calculator, the second function key of the log button is the 10 to the x power. Now, way back when I was in school, we called that the anti-log. It was the reverse of the log. And I think these days they don't call it that. It's just 10 to the x. So if you have the hydrogen ion concentration, or if you're trying to find the hydrogen ion concentration, and you have the pH, you use this little formula, and that 10 to the x key on your calculator, 10 to the minus pH. And the formula for the hydroxide ion concentration looks exactly the same, 10 to the minus POH. Now, we don't use this formula very often, but it's also true of a solution, that if you take the hydrogen ion concentration times the hydroxide ion concentration, they will always multiply together to be 10 to the minus 14. By the way, the negative log of 10 to the minus 14 is 14. Okay. Now we're going to practice using our calculators just a little bit. You have some practice questions here. Find the log of these. And the first one you're given is 1 times 10 to the minus 5th. So on my calculator, I just turn on and 1 EE minus 5. So I enter that. And then I just push the log button. Now it gives me a negative number. It's negative 5. So what that's telling you, well, first of all, before we talk about what that's telling you, you need to be able to, on your calculator, take the log of 1 times 10 to the minus 5. Now, my calculator, you entered the 1 times 10 to the minus 5 and you pushed the log button. Some calculators, you push the log button and it will come up in your screen with a little log and a square for you to enter a number. And so you first push the log button and then enter the 1 times 10 to the minus 5. So figure out how your calculator does it. You should come up with minus 5. Now we'll practice with another one. 7.8 times 10 to the minus 9. So clear. 7.8 EE minus 9. You know, my calculator, you put the number in and then push the log button. Yours might work the reverse of that. We're getting this number minus 8. I'm going to call that minus 8.1. We're going to talk a little bit later about significant figures and pH. For right now, I'm not worried about that too much. Okay, now these both came out to be negative numbers. When you have a small number and you take the log of it, it will always be a negative number. Well, old Sorensen didn't like negative numbers. He wanted the pH scale to be positive, so that's why these formulas have a negative sign in front of them. It's just to make these numbers positive. Now, let's do the reverse. So we're going to be taking 10 to the minus 4.5 power here. So on my calculator, I enter minus 4.5. So there's, it wasn't coming up minus 4.5. So now I have minus 4.5 here, and I hit the second function, 10 to the x key, and I get a real small number. Now, if you don't like, you will always get a real small number when you're taking something to a negative power. So if you don't like zeros, put it in scientific notation. In my calculator, that's done like this, and that's 3.16 times 10 to the minus 5. And you might pause the tape here and make sure you can get with your calculator the same number I got. So let's try another one. This time we're doing 10 to the minus 6.7 power. So enter 6.7, at least the way you do it on my calculator, negative. The most common mistake people make is they, just like I did, they forget or don't do correctly the negative sign. So take your negative 6.7 and then your 10 to the x key, and mine came out 1.995. I'm going to call that 2.0 times 10 to the minus 7. Now, if you don't have your calculator in scientific notation, it's going to be 0.00000 something 2. So usually it's easier to deal with these concentration, these real small numbers in scientific notation. Okay, now let's flip over the page. We've learned that pH is equal to minus the log of the hydrogen ion concentration, but what does it mean? Well, if you have pH that's exactly equal to 7, you have a neutral solution. If you have a pH that is less than 7, and by the way, it needs to be exactly 7. So 7.0, 7.1 would not be neutral, or 6.9 would not be neutral. If your pH is below 7, you have an acidic solution. An acid or an acidic solution, either way you want to say it. If you have a pH of greater than 7, then you have a base or a basic solution. So let's work some problems. First of all, what is the pH of a solution whose hydrogen ion concentration is 5 times 10 to the minus 8? So I do clear my calculator here. 5 EE 8 negative. Okay, so I've entered 5 times 10 to the minus 8 in my calculator, and I just push the log button. Let me rewrite the formula just so you remember. pH is equal to minus the log of the hydrogen ion concentration. So when you take the log of this number, now I'm in scientific notation, but you always get a negative number, but remember the formula has the negative in front of it, so the pH will always come out to be a positive number. So 7.3 is the pH here. Now, it didn't ask me for the pOH, but if it did, all I have to do is go back to this formula. The pH plus the pOH always add to be 14. So if I'm given one of these, I can always find the other by subtracting from 14. So 14 minus 7.3 is going to be 6.7. That would be the pOH. They didn't ask for it, but that's how we would find it. Okay, now our next problem is, what is the hydroxide ion concentration of a solution whose pOH is equal to 12.3? Well, from that formula from the other page, the hydroxide ion concentration is equal to 10 to the minus pOH. Okay, so that would be 10 to the minus 12.3. So again, take my calculator. 12.3 negative 12.3, 10 to the x function, and I get 5.01 times 10 to the minus 13. So if you don't get a small number, one with a negative exponent, it usually means that you forgot the negative sign when you did your 10 to the x function. So that's important. Now, our third problem here says, what is the pOH if the hydrogen ion concentration is 3.75 times 10 to the minus 10? Our formula for pOH is equal to minus the log of the hydroxide ion concentration. But we don't have the hydroxide ion concentration. We have the hydrogen ion concentration. So for most people, the easiest way to do this is to first find the pH. pH equals minus the log of the hydrogen ion concentration. And since that's what we have, it's minus the log of 3.75 times 10 to the minus 10. So we just take our calculator, enter 3.75 EE 10 minus on my calculator. So I've entered the number and I just hit the log key and it comes out negative 9.4, but this negative makes it positive, so I get 9.4, I'm going to call it 9.43. Now don't forget, that is the pH that we just found. We need the pOH. So pOH is equal to 14 minus the 9.43. I'm using that formula, that pH plus pOH equals 14. So I take 14 minus 9.43 and I get 4.57 for my pOH. Now, let's see. Number 4. What is the hydroxide ion concentration if the pH is 9.5? Well, to get the hydroxide ion concentration, to use that formula, I need the pOH. So again, I can get that just by subtracting from 14. So the pOH is equal to 14 minus 9.5. So 14 minus 9.5 is equal to 4.50. That is the pOH. So the hydrogen ion concentration formula is hydrogen ion concentration is equal to 10. It's going to give us our answer. So we want to take and enter minus 4.5 and then the 10 to the x key, and we get 3.16 times 10 to the minus 5th. That is our hydroxide ion concentration. Now we're being asked, number 5 here, which ones of the above, and 1 through 4, are acids and which ones are bases? Well, to do that, we need to know the pH. So if we go back to number 1 here, the pH is 7.3. That's greater than 7. So since it's just a little bit greater than 7, but it's greater than 7, so that makes it a base. And in number 2 here, we're given the pOH as 12.3. The pH is 14 minus 12.3. So 14 minus 12.3 is equal to 1.7. So since the pH is less than 7, this is an acid. Now you can also remember that anything with a pOH of greater than 7 is an acid, but that almost always confuses people. It's almost always less confusing to find the pH, and then if the pH is less than 7, you have an acid. All right. And number 3, the pH was 9.43. That's greater than 7, so number 3 would be a base. Number 4, The pH, this one is 9.5. 9.5. So, since that's greater than 7, this one would be a base. All right, now, I promised you we'd talk about significant figures in pH. A pH to 1 decimal place, like, say, 5.2, corresponds to a concentration known to 1 significant figure. A pH of 2 decimal places, like, say, 5.22, that corresponds to a concentration with 2 significant figures. So, in other words, the part of the pH that's to the left of the decimal point, like the 5 here, that has no effect on significant figures. You just count the decimal points of the pH, and that's how many significant figures your hydrogen ion concentration should have. And the same applies to looking at the pOH. You count the number of decimal places, that's how many significant figures your hydrogen ion concentration has. Now, that's more for the people that really get into significant figures. Here's the real bottom line. If you have pH and pOH, for the problems that we do, you should always report to at least 1 decimal place. There's a big difference between 6.1 pH and 6.0 pH. So always give at least 1 decimal place, and oftentimes 2. Okay, now measuring pH. The oldest way to measure pH, and it's been around for I think thousands of years. They used to take different kinds of lichens and squeeze the juice out of them and make something called litmus paper. You've probably heard of litmus test. It's a common word, but it comes from litmus paper. It's paper that's been dipped in this lichen juice, and it comes in either red form or blue form. Okay, and I don't have any at home, so I can't show you. But if you take a piece of red litmus paper and you stick it into a base, it will turn blue. So I just remember, base turns blue. Red litmus paper turns blue in a base. And then litmus paper also comes in blue. If you put it in acid, it will turn red. And you have to kind of say this with a Kentucky accent, but acid turns red is one way of remembering that. Blue litmus paper turns red in an acid. So all litmus paper tells you if it's an acid or a base. It doesn't tell you what the pH is, just acid or base. So that's not real useful. Sometimes it's useful, but not as useful as knowing the pH. This chart comes out of your book. It's a chart of pH acid-base indicators. Now, these indicators, and you've got a list of several names of them, they're usually themselves weak acids or weak bases, and they change color at different pH. So, thiamyl blue is an example. It's red at a pH down in the very low range, from 0 to about 2. It starts turning orange, and then it's yellow when it gets closer to 3. Now this indicator also changes color again at high pH, so it's yellow up to a pH about 8, and then between 8 and 9 it starts turning to a green, and then at pH 9 it's blue. So if you use that indicator and your color came out to be yellow, you would know that you're somewhere between a pH of about 2 and a pH of about 8. Others turn corner. Let's see. Another one that we will use, or we would use if we were back in school, would be bromothiamyl blue, also called PTB. It's an indicator that's yellow until about a pH right about 7. It turns from yellow to green and then blue above 7. So if you're trying to figure out when a solution is neutral, this is a good indicator to use because it starts changing color right about pH 7. Another real common one, it's hard to spell, it's called phenolphthalein, and it's an interesting indicator because it's completely colorless in an acid, and then at about pH 9 it turns into this brilliant pink color. Okay, it's commonly used because of that brilliant pink color. But anyway, these liquids come, these indicators come as a liquid. You can just put a few drops of them in your solution, and then depending on what color your solution turns, you can tell whether you're acid or base. Or you can get paper. Those of you who have pools or hot tubs at home probably have pH paper. And pH paper just has a combination of indicators that have been dried onto it. And you dip this paper into your solution, and it will turn color, and then your solution usually comes in a box or a bottle that has a color code on the outside of it, and you match the color up with the color code, and that tells you approximately what the pH is. Now, this isn't going to give you a real precise number, but it'll tell you if the pH maybe is 10 versus 8 versus 7. These days, a very common way of measuring pH is with a pH meter. It's a digital meter that you just stick a little wand into your solution, and it will digitally read out the pH. If you take AP chemistry, you'll use a pH meter. So those are the primary methods for measuring pH, either using the litmus paper, which only tells you acid or base, and a liquid indicator solution, or pH paper, which has the indicator solution dried onto it, or a pH meter.